The singularity represents the initial state of the universe, as described by the Big Bang Theory. It is theorized as an unimaginably small point containing all the matter, energy, space, and time of the universe compressed into infinite density and temperature. Unlike anything in the universe today, the singularity existed beyond the concepts of space and time. In this state, time as we understand it did not exist, meaning questions about what happens before the Big Bang are complex and perhaps meaningless in the framework of conventional physics. The singularity's infinite density implies that all the mass of the universe was concentrated into a point with no volume. This extreme concentration creates a paradox where our understanding of physics, including general relativity, breaks down. Infinite temperature also characterizes this state, where no known form of matter or energy could survive in a stable condition. These conditions exceed the reach of our current physical theories, which are incapable of describing what truly occurred in such extremes. Theoretical physicists believe that the singularity's conditions necessitate a unification of all fundamental forces. At such a high-energy state, gravity, electromagnetism, and the strong and weak nuclear forces likely existed as a single unified force. As the universe began to expand from the singularity, these forces separated during the rapid cooling process. This phase transition played a crucial role in shaping the fundamental laws of nature. Modern physics struggles to reconcile general relativity, which governs large-scale cosmic structures, with quantum mechanics, which describes the behavior of particles on the smallest scales. The singularity lies at the intersection of these domains, creating the need for a unified theory, such as quantum gravity, to explain it. Without this unified framework, the singularity remains an enigmatic concept that challenges our understanding of the universe. The singularity is often compared to the centers of black holes, where matter is also thought to collapse into infinite density. However, the Big Bang singularity differs in that it led to an outward expansion, giving rise to the universe itself, rather than remaining confined within an event horizon. This expansion, known as cosmic inflation, occurred in the first fraction of a second after the singularity, allowing the universe to grow exponentially and cool rapidly. The earliest measurable moment in the universe's history is called the Planck epoch, occurring /10⁻43 seconds after the Big Bang. During this brief time, the universe remained in an extreme state, and it is only after this epoch that current physical theories begin to apply. The singularity itself lies outside these theories, making it a purely theoretical construct. Mathematical models, including string theory and loop quantum gravity, attempt to describe the singularity. These speculative frameworks aim to address the breakdown of physics under such extreme conditions. Some propose that the singularity might not represent a true beginning, but rather a transition phase, possibly linking our universe to others in a multiverse or a cyclical cosmology. The idea of the singularity raises profound philosophical and scientific questions. If the universe originated from this point, what caused it to exist? Was it a one-time event, or is it part of an eternal cycle? The singularity also invites questions about the nature of reality itself, challenging the very boundaries of human knowledge. The cosmic microwave background radiation provides indirect evidence of the Big Bang, but does not offer direct insights into the singularity. Instead, it represents the residual heat from the universe's rapid expansion, occurring long after the singularity phase had passed. Observations of this radiation confirm the universe's dynamic evolution, but leave the nature of the singularity shrouded in mystery. Despite its central role in cosmology, the singularity is a concept more rooted in mathematics than in empirical science. It serves as a theoretical starting point rather than a physical reality that can be observed or measured. This limitation underscores the challenges of understanding the universe's earliest moments. Speculative theories about the singularity's nature include the possibility of it being a gateway to a multiverse or part of a bouncing cosmology, where the universe alternates between expansion and contraction phases. These ideas remain unproven but highlight the diverse possibilities being explored by scientists. The singularity also challenges the distinction between science and philosophy. Questions about why the universe began and what existed before its origin transcend physical theories, delving into metaphysical and existential realms. This intersection of science and philosophy underscores the singularity's broader implications for human understanding. Although the singularity is central to the Big Bang Theory, it remains one of its most mysterious and least understood aspects. Scientific progress may one day shed light on this enigmatic state, but for now, it represents a boundary of knowledge where imagination and inquiry intersect. The singularity as a concept reminds us of the vast unknowns still present in cosmology. It symbolizes not only the beginning of the universe, but also the limits of human understanding, urging further exploration into the origins and nature of existence itself.
The term Big Bang describes the beginning of the universe as a rapid expansion of a singularity approximately 13.8 billion years ago. This event marked the origin of everything we observe today: space, time, matter, and energy. Unlike a conventional explosion, the Big Bang was not an outward blast in a pre-existing space. Rather, it was the sudden expansion of space itself from an infinitely dense and hot point. In the first moments after the Big Bang, the universe was an incredibly small, hot, and dense state. Known as the Planck epoch, this phase lasted only (10⁻⁻43 seconds. During this time, the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were unified. As the universe expanded and cooled, these forces began to separate, shaping the physical laws that govern the cosmos today. The rapid expansion known as inflation occurred immediately after the Planck epoch, causing the universe to grow exponentially in a fraction of a second. This inflationary period smoothed out irregularities and set the stage for the formation of large-scale structures like galaxies and clusters. Without inflation, the universe would have been too chaotic for these structures to form. As the universe continued to cool, fundamental particles like quarks, electrons, and gluons emerged. Quarks combined to form protons and neutrons, which later became the building blocks of atomic nuclei. Within minutes of the Big Bang, nucleosynthesis began, forming the first simple elements, primarily hydrogen and helium. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form. This event, known as recombination, allowed photons to travel freely, creating the cosmic microwave background, CMB, radiation. The CMB is a faint glow permeating the universe and serves as a snapshot of its early state, providing strong evidence for the Big Bang Theory. As matter began to clump together under the influence of gravity, the first stars ignited, creating heavier elements through nuclear fusion. These stars later exploded as supernovae, dispersing these elements into space, enriching the universe with the materials needed for planets and life. This process marked the beginning of stellar and planetary evolution. The Big Bang also marked the origin of time itself, as there was no before the Big Bang in the conventional sense. Time and space were created in the event, fundamentally altering our understanding of causality and existence. This idea challenges human intuition and remains a topic of philosophical and scientific exploration. One of the most striking pieces of evidence for the Big Bang is the ongoing expansion of the universe, discovered by Edwin Hubble in the 1920s. He observed that galaxies are moving away from each other, with their speeds proportional to their distances. This redshift phenomenon aligns with the idea of a universe that started from a single point and has been expanding ever since. The Big Bang Theory also explains the abundance of light elements like hydrogen, helium, and lithium in the universe. The observed proportions match predictions made by nucleosynthesis models based on the early conditions of the universe. This agreement reinforces the theory's validity. Despite its successes, the Big Bang Theory does not address certain questions, such as what triggered the expansion or what, if anything, existed before it. These unanswered questions lead to speculative ideas like multiverse theories, which suggest that our universe might be one of many born from similar processes. The theory is also complemented by the discovery of the cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson. This radiation, a relic of the Big Bang, provides a detailed map of the early universe's temperature fluctuations, revealing the seeds of cosmic structures we see today. The Big Bang not only set the stage for the physical universe, but also established the arrow of time. The universe's expansion and increasing entropy provided direction for time, shaping the evolution of matter, energy, and life itself. The concept of the Big Bang continues to inspire both scientific investigation and philosophical inquiry. It raises questions about the nature of reality, the origins of the cosmos, and humanity's place in the vast expanse of existence. These questions bridge the gap between empirical science and metaphysical thought. While the Big Bang Theory remains the most widely accepted explanation for the universe's origin, it is not without its limitations. For instance, it does not explain dark matter or dark energy, which make up most of the universe's mass and energy. Future discoveries may refine or expand our understanding of this monumental event. The Big Bang represents not only the birth of the universe, but also a profound reminder of how far humanity has come in understanding its origins. It is a cornerstone of modern cosmology, inspiring us to continue exploring the mysteries of existence and the forces that shaped our universe.
The concept of infinite density at the singularity is one of the most profound and perplexing aspects of the Big Bang Theory. Infinite density means that all the mass, energy, and matter in the universe were packed into an infinitely small point with no volume. Essentially, everything in the cosmos existed in a state where space itself was collapsed. This point is often described as a singularity, where the laws of physics as we understand them break down entirely. The singularity represents a state in which the universe's mass is compressed to an extent so extreme that conventional concepts like volume, space, and time lose all meaning. In classical physics, matter is understood to have mass and volume. We intuitively think of objects as occupying space, and gravity is the force that governs how mass interacts with the fabric of spacetime. However, when we consider infinite density, we run into a paradox. How can an object possess infinite mass in a point with zero volume? Such a state defies all common experience and challenges even our most fundamental laws of physics. The breakdown of physics at the singularity arises because the equations of general relativity and quantum mechanics fail to describe conditions with infinite density. General relativity describes how mass curves spacetime, and it works exceptionally well at large scales, such as the movement of planets, stars, and galaxies. However, when dealing with a singularity, the curvature of spacetime becomes infinite. The equations of general relativity cannot handle such extreme curvatures, resulting in a breakdown of our understanding. The laws that describe the behavior of gravity at this scale are inadequate, and we can no longer predict what happens when mass and energy are packed into such a small, dense point. On the quantum mechanics side, the laws that govern the behavior of tiny particles, such as electrons and quarks, also fail to work at the singularity. Quantum mechanics operates on the very smallest scales of energy levels of atoms and subatomic particles. At these scales, particles behave in probabilistic ways, and uncertainty reigns. Yet, quantum mechanics does not account for the extreme curvature of spacetime present at a singularity. The interaction between gravity and quantum mechanics, which becomes critical under such conditions, is not fully understood and is not reconciled in current theoretical physics. The failure of both general relativity and quantum mechanics to explain the singularity has led to the search for a new theory, quantum gravity. Quantum gravity is the elusive theory that would unify general relativity's description of gravity with quantum mechanics' explanation of subatomic behavior. It is expected that this new theory will be able to describe conditions at the singularity and reveal the true nature of infinite density. However, despite extensive research, quantum gravity remains one of the most difficult and unsolved problems in modern physics. The presence of infinite density creates a paradox. For one, it suggests that the mass of the entire universe, everything that exists or has ever existed, was once concentrated in a space so small that it essentially had no size. How could such a state of affairs come to be? Furthermore, this infinite concentration of mass also means that the gravitational field at the singularity would be infinitely strong. Such extreme gravity would distort spacetime to an extent beyond anything we can directly observe. These conditions are simply beyond the reach of current experimental methods and make it nearly impossible to probe the singularity directly. A critical issue with the singularity is the notion of time. The singularity existed in an environment where time, as we understand it, may not have functioned. In conventional terms, time is linked to the flow of events. However, in the singularity, where all matter and energy were packed into an infinitely small point, it is possible that time itself did not exist in any conventional sense. The very beginning of the universe, as we understand it, would have emerged when time itself began. A concept that is deeply challenging for our traditional models of physics. Many theoretical physicists have proposed that the infinite density at the singularity is a symptom of the limits of our understanding. One possibility is that at extremely small scales, space and time may behave in ways that are fundamentally different from our conventional experience. Ideas such as string theory and loop quantum gravity have been developed to explain how space and time might be quantized at these extreme scales. These theories suggest that rather than the infinite density we expect from a singularity, the universe may have undergone a different process entirely, possibly involving a discrete structure at the smallest levels of reality, where the notion of a singularity does not even apply. Other theories suggest that the infinite density at the singularity could represent a point where the fabric of space-time itself undergoes a transition, perhaps creating a new set of physical laws. This has led to speculations about the possibility of bounce cosmologies, where the universe repeatedly contracts and expands, never truly beginning or ending. According to this view, the Big Bang may not have been the first event in the universe's history, but rather one phase in an ongoing cycle. Despite the speculation, the core issue remains that infinite density represents a breakdown of physics at the most fundamental level. At such extreme conditions, we are confronted with the limits of our current understanding of nature. Infinite density suggests that the universe was in a state that is fundamentally different from anything we can observe today, forcing us to question the very nature of reality. It's possible that the answer to what occurs inside a singularity could revolutionize our understanding of the universe, but for now, the nature of infinite density remains one of the most profound mysteries in modern cosmology. One of the most pressing questions is whether the infinite density of the singularity represents a true physical state, or if it is simply a mathematical artifact, an indication that the theories we are using are not yet complete. Some physicists believe that the singularity is not a real point of infinite density, but rather a signal that we need a new theory to explain such extreme conditions. In this case, infinite density could be an artifact of our inability to fully describe what happens under such conditions. In trying to understand the singularity, scientists and philosophers alike are forced to confront fundamental questions about the nature of time, space, and reality. The infinite density of the singularity challenges our conception of existence itself, forcing us to consider the possibility that the universe could have originated from a state that is fundamentally different from anything we can currently imagine. It may also suggest that the universe itself could be part of a larger, deeper structure that we do not yet understand. While infinite density remains one of the most puzzling and complex concepts in modern cosmology, it is also one of the driving forces behind current research in theoretical physics. Understanding the singularity and its infinite density could ultimately unlock a new era of scientific discovery. Until then, it serves as a reminder of how much we still have to learn about the origins of the universe and the nature of the reality in which we live. The search for answers to the questions posed by infinite density continues to inspire some of the most cutting-edge research in science today, as physicists seek to understand the very fabric of the universe.